Acidity is such a common and important aspect of solution chemistry that we have a simpler scale for keeping track of it, pH. The H stands for the concentration of free hydrogen ions, what we've been calling hydronium, and the P just means that we take its negative logarithm. So pH is the negative logarithm of the concentration of hydronium in solution. To write that in reverse, it means that the concentration of hydronium in solution is 10 to the negative pH. That means that when we add 0.005 moles of hydrochloric acid to 1 liter of water, we produce a 2.30 pH solution. That's the negative log of 0.005 because we can assume that the hydrochloric acid separates completely. If we add 0.006 moles of sodium hydroxide to 1 liter of water, then we get a negative log of 0.006 or 2.22 POH solution. Now, don't get confused, this isn't pH. We're looking now at the scale in terms of the base, POH. So what happens when we combine these two solutions? One a solution of hydrochloric acid and one a solution of sodium hydroxide. Initially, we have 0.005 moles of hydronium. Then when we add 0.006 moles of hydroxide, we know that that's going to react with the hydronium to make water. In this case, the acid is the limiting reagent. So for 0.005 moles of acid, we make 2 times that, or 0.01 moles of water, and we're left with some hydroxide. In fact, we're left with 0.001 moles of hydroxide in 2 liters of water, because remember, we mixed the two solutions together. So this makes a solution with the POH of negative log of 0.001 divided by 2, or 3.3 POH solution. Now normally we don't keep track of it in terms of the concentration of hydroxide, and instead we move it into pH. And we can do that pretty easily because we already know that water is going to maintain an equilibrium constant of 1.0 times 10 to the negative 14 as the product of the concentration of hydroxide and hydronium in solution. So we can calculate the concentration of hydronium because 0.0005 times the concentration of hydronium will equal 1.0 times 10 to the negative 14. Or we can simplify things a great deal by using the rules of logarithms and just subtracting the POH from 14 to find the pH. So in this case, we have 14 minus 3.3 equals 10.7. And the pH of the solution is 10.7. That's above 7 on the pH scale, so the solution overall is basic, or alkali. So how much more of the 0.005 molar acid solution would we need to add in order to neutralize the overall solution? We need to add enough more acid to react with all of the hydroxide, but no more. Since there is 0.001 moles of hydroxide in solution, then we need to add 0.001 moles of hydronium to the solution. And here's where we can use the concentration as a conversion factor between moles and volume. We multiply the amount that we want by 1 liter per 0.005 moles to determine that we need to add 0.2 liters of the acid solution, leaving us with 2.2 liters of salty neutral water.